Hi all, today I'm going to be going over the recitation group work. So the first thing is to start with a diagram of key reactions from chapter 12. And actually, the reason we do this is not just to, torture you or give you more busy work. It's because a lot of times in organic chemistry, the information is presented and it can seem like just like a long list of reactions. Like, know all these reactions and just memorize them all, when really you'll be able to memorize or understand, I guess, not even memorize them better if you break them down into chunks or organize them. So, like, for a phone number, you don't just memorize the whole 10 numbers, you break them down into chunks. And so we want you to do that as well with your organic chemistry work. So that's our goal, is actually for you to understand how to organize the reactions better. And that way you can understand kind of what they're doing and not just memorize a super long list. So if you look here, I can show you how I organized my list. So this is a reduction / oxidation. Sorry if you can hear the clicking and the typing in the background. I'm sharing a desk with my husband because it's a snow day, so we're both working from home. So for reduction and oxidation here, I've defined them. So here's my definition. One makes more bonds to hydrogen, one makes more bonds to oxygen. And then I've done like sort of a note of like, okay, so from carboxylic acid plus a hydrogen to an aldehyde plus a hydrogen to an alcohol, that's reduction. Going the other way, alcohol plus an oxygen to aldehyde plus an alcohol to carboxylic acid is oxidation. So then I was like, okay, those are the big things, oxidation and reduction. So for reduction, we have two main reagents, LAH and NABH4. LAH can reduce any of the things listed here, where NABH4 can only reduce aldehydes and ketones. So then I have the process of reduction for each of those. So carboxylic acid goes to an aldehyde and then to an alcohol. Same thing with an ester, alcohol and then aldehyde, or aldehyde then alcohol. And then for a ketone, it goes straight to an alcohol, but that is a secondary alcohol. An aldehyde, which we saw over here already, goes to a primary alcohol. So these all result in primary alcohols. Ketones result in secondary alcohols, and the reason for that is because they already have two carbons there. I talked about that on my video on TikTok. Is basically you need a bond to a hydrogen to add. You can't break a carbon-carbon bond to add extra hydrogens in, if that makes sense. And then I did the same thing here with with oxidizing. Here's all the reagents. There's chromic acid, PCC, and KMNO4, and then I put all my notes on them. So like chromic acid is also called Jones reagent, and this is what Jones reagent looks like. It just basically makes the chromic acid in situ, and it takes carboxylic acid from a primary alcohol. It makes carboxylic acid. From a secondary, it makes a ketone, and there's no reaction with tertiary alcohols ever. And this is the one that starts out as orange, and if a ketone is created, it turns green, or if a carbon-oxygen double bond is created, it turns green. And then same thing with PCC, aldehyde. It does not go all the way to carboxylic acid. Even if you start with a primary alcohol, that makes it slightly different. And then ketone, and no reaction for a tertiary. And then KMNO4 acts a lot like chromic acid, but remember KMNO4 with a double bond will cleave that double bond, and KMNO4 that's cold will actually just only cleave one bond and add two alcohols. And then I did a little overview. So it's like primary alcohol to aldehyde to carboxylic acid. PCC is only strong enough to do this first step, but both Jones reagent and KMNO4 will go all the way to the carboxylic acid. Secondary alcohols always stop at ketone because you can't add another oxygen bond. You can't break a carbon-carbon bond, and for that same reason, tertiary alcohols never react. So that's pages and pages of PowerPoint notes that I've just condensed down into 2 pieces of notebook paper. I could have done even less if I had better handwriting. Whatever makes sense to you as how you want to organize your notes, I really want to encourage you to do that, because it's going to help you understand the material a lot better if you take the time to organize your notes and to understand what does what or what's different between different reagents. That's a big key to understanding organic chemistry better and succeeding in the class. And then the other thing I went over for chapter 12 was grignard reagents. So grignard is a way to get carbon-carbon bonds to form. You start out with an alkyl halide, alkyl bromide preferably. You add magnesium metal. You'll get an opportunity to do this in your lab, which is really cool. And it essentially acts as a nucleophile with a carbon anion, basically. So instead of having like MgBr, it's more similar to like this carbon bond negative. Oh, sorry, that might help so you don't get the shadow. This carbon bond negative, and then the MgBr as positive. It's more similar to that than actually a true bond being formed there. It's more like an ionic bond. And then that negative charge will act as a nucleophile. So you may see it act in opening an epoxide. You may see it attack on the carbon-oxygen double bond, or you may see it attack in an ester. Then one other thing I want to go over with you, which I think is actually really important and shows up for a lot of it's in chapter 11, chapter 12, and then it comes back up in like, I think chapter 16, 17, and 18, is if you have a carbon-oxygen double bond and you don't have a good leaving group on either side, if it's just R groups, and the nucleophile comes in and attacks, it'll kick it up. The same first step is true if you do have a good leaving group. So like for an ester, that's a good leaving group. The nucleophile will attack and kick it up. And both of these result in an O minus because the bonds in the electrons in this bond broke and came up here, and the nucleophile is down here below. And then same thing here, O minus, because the electrons in this bond moved up to the top as a new bond formed, because you can't have more than 4 bonds to that carbon. But if this one has a good leaving group, these electrons can actually come back down and reform your carbon-oxygen double bond, and then the leaving group will leave. And you'll end up with this, and your nucleophile can attack again. And we've seen that with Grignard reagents and esters that this will happen, but it actually happens with any good nucleophile and a good leaving group. And you end up with 2 of your nucleophiles attached. So this idea that if you have something negative, like some kind of nucleophile, and then a carbon-oxygen double bond, usually the nucleophile is going to attack right there, and you're going to get an alcohol. If one of them is a good leaving group, like an ester, it will attack twice. You should learn this and become familiar with this because it happens a lot in OChem too. We're about to kind of switch gears and go into a slightly different topic in, I can't remember the word for some reason, resonance and conjugation and aromatic rings. So we're going to shift gears a little bit, but then this is going to come back up. So I really encourage you to have this in your mind. And if you were paying attention, this is the same thing that happens with if you have LEH. It's basically just like an H minus that comes and attacks, and that's how it turns a ketone into an alcohol, is you have that plus H plus to make this into an alcohol. So you're going to see this same pattern of a nucleophile attacking at the carbonyl carbon center a lot. So I just kind of wanted to bring that to your attention. So that's 3 pages to summarize the main points from the whole chapter. And once you have that, when you're working through practice problems, like in the group work, if you find something that you missed, then you can go back in and add this in. So for example, I made all of my oxidizing reagents list, and then I saw the question about color changing, and I was like, oh yeah, I should add that in. So try to kind of, if you see a hole in your notes, you can go back and add it in, but this is a great place to start where you have a good basic idea of everything that's going on in the chapter and you've organized it in a way that makes sense to you. Okay, so that's just a little bit of a study tip for you. Let's start in on the actual practice problem. So defining oxidation and reduction in organic chemistry, well, actually, I already did that. Oxidation is more bonds to oxygen, or another definition is more bonds to something more electronegative than carbon. Carbon's kind of in the neutral there, so that's oxidation. And reduction is more bonds to hydrogen, or more bonds to something less electronegative than carbon. And then we can go down here and apply this to a practice problem. So when I'm looking at these 2 carbons are the only ones that are changing. So we can look at those and determine how many bonds these have to something more or less electronegative than carbon. So this has 2 bonds to oxygen, so that's more electronegative than carbon, 2 bonds to oxygen. So that is already, to me, standing out something that is going to be in the highest level of oxidation. Next, this has 2 bonds to hydrogen, which are less electronegative than carbon. But over here we have 4 bonds to hydrogen. So we've increased the number of bonds to hydrogen. So this is the most reduced, and this is the most oxidized. And this is more like neutral. It's in the middle. It does have some bonds to hydrogen, but it has the one bond that's changing is now 2 carbon bonds. So, and the question asks us to list these in order of increasing oxidation. So we start with the most reduced, so 3 first, and then we get 1, and then 2 is the most oxidized. I might put my arrows backwards, like 3 is the least, and then 2. Least oxidized. And you can also do these with oxidation numbers if you want, but I don't always remember which numbers are assigned to which, which, like, oh, I think hydrogen is -1 or is hydrogen +1. Like, I can mix that up for myself pretty easily. So I'm not good at like just positives and negatives like that. So it's easier for me to think of it this way. But Dr. Krauss went over how to do it in terms of the numbers of oxidation states in class. But I would only do it for these carbons that are changing. The rest of them are staying the same, so you don't have to do it for all 5 carbons. Okay, so the next question is draw the general mechanisms for the following reaction, LAH and NABH form. So what I do when I see these, and this should be acceptable on your quizzes and exams, is I just consider these to act as an H-. Basically, they generate H- in solution. So if you have a ketone or an aldehyde, and you have H-, this is the exact reaction I talked about before. It will attack here and form a 5th bond to carbon, but you can't have 5 bonds to carbon, so one of these will break. And the reason it chooses actually to do that is because there is a resonance structure where that's negative and this is positive, right? So there's already, in resonance, is 2 structures existing actually as a hybrid of the 2. It's not 2 separate ones. So there's always a partial negative up here and a partial positive right here. So that's where the nucleophile wants to attack. So that's why it attacks right there. And this bond breaks is because it's already like on its way to being able to do that. And then you have your O-, and the new bond to hydrogen has formed. And then you add acid to neutralize that negative charge there. And you'll get an alcohol with your hydrogen down below. You don't have to draw on that hydrogen. You can just do it as a secondary if you want, and not actually draw on the hydrogen because that hydrogen's implied. Those act basically as the same thing. So that's the general mechanism actually for both of them. If you want to use LAH and NABH4 fully written out, that's fine too. I typically don't, and that is still considered an appropriate mechanism. Okay, and then which carbonyl containing compounds are each reagent above able to reduce? So, and if you'll notice, when we summarized all of our notes, we talked about LAH and NABH4 reacting this way when we went over Grignard reagents and nucleophiles. And we also summarized in our notes which reagents reduce which. So if you're able to summarize your notes, then it's much easier to get through practice problems like these. So NABH4 can only reduce aldehydes and ketones. LAH can reduce those plus carboxylic acid and esters. So I'm actually just going to draw out this thing because this is how I remember it. And if this question ever comes up on a test, I just usually have this drawn on the exam. Like as soon as I get the test, I do this to help me remember. And there you go. LAH reduces all of these, and NABH4 only reduces these 2. All right. Show how you would prepare the following Grignard. Well, basically, Grignard reagents just start with some kind of alkyl halide, and you add in an Mg. We also summarized that in our notes. So this is why we ask you to create a note summary, is because we're hoping you kind of can create an overview and then go back in and see what your understanding is and where you missed. So we I did a general Grignard reagent where basically it starts with some kind of carbon chain with a bromine, and then you add magnesium, and that generates your Grignard reagent, which is essentially this. So another way to say this is Rx, so carbon chain with any halogen, plus Br is going to get you RMGX. X just stands for any halogen, and R just stands for any carbon chain. So if you had bromine right there, you could add magnesium in, and it would get you MgBr. And really, that acts more like if this carbon right here was a carbanion, so it acts as a nucleophile. And the main function of Grignard reagents, they act as a nucleophile to form carbon-carbon bonds. That's the biggest thing they do, is form carbon-carbon bonds. It's a way to turn your carbon into a nucleophile and then attack another carbon. And Grignard reagents can act on expoxides, basically anything with a nucleophile, where a nucleophile would attack that you've seen before. It can act in SN2 reactions if you have the proper conditions for it, so no protons. It'll still any available hydrogen if you have an acidic hydrogen. So basically, from carbon-carbon hydrogens, it's like a pKa of 25 and more acidic than that. So if you have an alcohol, it'll steal that. If you have pKa of 25 or lower, anything more acidic than a pKa of 25, it'll take that. And it can also act on carbonyl carbons to form a carbon-carbon bond at the center. So I have it drawn like this, but we had it over here more looking like that. And the nucleophile will come and attack right there. And then last but not least, why must it be prepared in dry conditions? Well, because of this right here, if it will react with anything with a pK more acidic than 25, there can be no water. That's what we mean in organic chemistry when we say dry. That means no water, because water's pK is 15.7, so a Grignard reagent will take that hydrogen. So if you had, let's just say this Grignard reagent that we had up here, plus water, and this pKa is 15.7, so it's going to take this pKa and react, and you'll end up with the hydrogen bonded right there. There's 3 hydrogens, but the other 2 were already there, plus OH minus. So that's why it can be prepared in conditions where there's water. Okay, if we have, I'm going to draw in the hydrogen because it's easier for me to see. LaH, I just do that as H minus. It's going to come and attack and kick up. And so we'll get O minus. There was an H already there from the aldehyde and another H already bonded. Another H bonded right here. The electrons from this H minus formed a bond between this carbon and this hydrogen. And then we have H plus. So that adds a hydrogen to this oxygen, and you end up with an alcohol. So that's just the generalized reaction mechanism for LaH that we talked about on the previous page. And I always make sure that I have the right number of carbons here because I tend to lose them. So, yep, there we go. Looks correct. Okay, next question is what happens if you react a secondary alcohol with PCC, basically. And I'm going to pull back out my notes on oxidizing agents. So PCC, if you have a primary alcohol, it takes it to an aldehyde. If you have a secondary, it takes it to a ketone. There's no reaction with tertiary, so it goes to a ketone. We also have that down here. Primary alcohol will go to an aldehyde with PCC. Secondary alcohol goes to a ketone, and that's for all Jones, PCC, and KMNO4. So if this becomes a ketone, it should look like this. 5-membered ring, that doesn't change. Just we go from an alcohol to a ketone. All right, so this is another type of organometallic reaction. I did not summarize it in my notes because it comes up a lot less often, so I think it's less important to have in your notes, but this would be a good opportunity for you to be like, oh, I'm missing something from my notes. I'm going to go back and add like a little star. Around Grignard reagents is a similar organometallic is if you had lithium with a halogen, it will do basically the same thing. And this basically acts the same way as a Grignard reagent, and this becomes a nucleophile. So it's very, very similar. I don't think it's similar enough to make a note of, but if you are going to forget, it may come up on a test, so it's worth it to check, but it doesn't come up a lot in organic chemistry. Okay, the next question is actually a reaction with a Grignard reagent, not just preparing the Grignard reagent. And a big thing here that I do is whenever I see a Grignard reagent, I will make this negative with MgBr positive. So this is just 2 carbons and one of them has a negative charge on it. So that's now your nucleophile. So this is a negative thing. So this is base catalyzed ring opening of epoxide. And hopefully you remember BLAM, so the base will attack the least substituted side. And I have a whole video on ring opening of epoxides. So it'll come and attack the least substituted side, and then this will break open. Now, one big thing that I do with these is number my reactions, because let me grab the pen I'm looking for. It's really easy to lose track of carbons here, so I always number the main ring. So this is carbon 1 and this is carbon 2. So when we draw them out, I'm just going to start with drawing carbon 1 and 2. 1 and 2. And then on carbon 1, we already had a methyl group. And then the ethyl group, 1, 2 carbons attacked, right? So that's 1, 2 carbons and the new bond formed right there. This bond broke. So on carbon 1, we no longer have a bond to oxygen, but there is still a bond to oxygen on carbon 2, plus 2 methyls. So this is what I end up with. So whatever makes sense to you, if you want to start the numbering out here, like 1, 2, 3, 4, that's fine, but make sure that you're not losing carbons, because as epoxides get more complicated, that is one of the biggest mistakes I see students making, is they understand the way the reaction works, but then they're not doing the right number of carbons, so then they just get points off for that, which is such a bummer, because if you understand the concept, we want to give you full points. And then you add H plus in the second step to turn this into an alcohol. I drew it a little weird, but that's still the right answer technically. I just did it kind of strange. And then in the last one, NaBH4, well, if you remember from our notes and from the last question, NaBH4 only reduces ketones and aldehydes. So this would actually be no reaction. If you did it with LAH, instead, it would reduce it down to a primary alcohol. So hopefully you remember that as well. All right, now this next question is difficult. It's more of a retrosynthesis question, and it asks, what reagents would you use to accomplish the following transformation? So I'm looking at this and I'm seeing a ketone go, or actually an ester go to an alcohol. So then I'm like, is it going to be reduction? Well, if it was reduction, then this whole group gets lost. Remember, esters go all the way down to primary alcohols. So if you just reduce this with like LAH, it would become this. You would have carbon 1, carbon 2, OH, and this whole group would have gone away. And that's not what we have. We actually have 2 carbon chains added on to this point right here. Carbon 1, 2, and right there at carbon 2, there are 2 new carbon chains added on. So when I see new carbon-carbon bonds formed, usually I think Grignard reagent. So that's the next thing we can ask. Grignard reagent reacts with ketones to make alcohols, and if it's a ketone with a good leaving group or a carbonyl with a good leaving group, it's going to attack twice, right? So that to me is a good sign that that's going to be a Grignard. And so the main reaction that I'm talking about here is the one I mentioned before. Your nucleophile will come and attack and kick this up. So you end up with an O- with a good leaving group in your nucleophile. Then this will come back down. It reforms the carbonyl and then the leaving group leaves. So now you have a ketone with your nucleophile. But if you have excess nucleophile, your nucleophile can come in and attack again. And because there's still a partial positive there, and then you get 2 additions of the nucleophile plus if you add H plus and alcohol. So that is what it looks like is happening here to me, is this is basically just a good leaving group. And if we have a nucleophile with 2 carbons, so actually this exact one that we had before, MgBr, that basically functions as 2 carbons with a nucleophile, it can come and attack, and you would get O minus with your good leaving group and your nucleophile of an ethyl. So 1 carbon, 2 carbon. Then this will come back down, reclaim, and kick this out. Because it is a good leaving group, it can leave. You have O with your nucleophile on there. But if you have excess of this MgBr, it can come in and attack again. So that's essentially just this. It'll come and attack, kick up, and you get O minus. And now you have 2 of your ethyl groups that have attacked, and then you would add H plus to turn that into an alcohol. So hopefully that makes sense to you. So the reagents I would use for this would be 1 excess MgBr, and if you want, you could start that just from being bromine plus Mg to make the reagent, and then 2, I would have H3O plus or some kind of acid. Okay, next question. Sorry, I thought I was going to sneeze. My allergies have been really bad today. Okay, so next question is, describe a test to distinguish between primary, secondary, and tertiary alcohols, or primary, secondary alcohols from tertiary alcohols. And this was when I wrote a summary of all my notes from the chapter, and then I went through and solved the group work by myself before I do a video, so I can make sure that I'm making a good video for y'all. And when I did that, I realized, oh, I did not make a note about chromic acid. So I'm going to go make a quick note about that. So chromic acid is orange, but when you react chromic acid with a primary or secondary alcohol and it turns it into a carboxylic acid or a ketone, it turns green. So there's a color change in that. And the reason for that is actually because there's a chromium ion that gets like kicked out after the oxidation happens, after the oxidation happens. So because of that, the chromium ion is green. So that's where it turns from orange to green. So because you can see that reaction happen if you have a primary alcohol that goes to an aldehyde, or actually it'll go all the way to carboxylic acid, or a secondary alcohol that goes to a ketone, it goes from orange to green because it makes a chromium ion. I think it's chromium 3. But can you do a reaction? Can you oxidize a tertiary alcohol? Hopefully you know at this point you can't. There's no reaction with a tertiary alcohol. So it's not going to turn from orange to green. It's going to stay orange. So if you had primary or secondary alcohol, it would go from orange to green. Secondary alcohol would go from an alcohol to a ketone. This one would be an aldehyde. This one would be a ketone. Tertiary alcohol, there'd be no reaction, so it never turns to green. It just stays orange. And that's how you can use the chemical test of chromic acid to tell between a primary, secondary alcohol and a tertiary. So this would come in handy if you were in the lab and you thought you had generated a tertiary alcohol, like maybe you were trying to do this reaction and you wanted to check and see if it worked. You could, if you could isolate just this tertiary alcohol and add Jones reagent to it, it should stay orange. Nothing would happen. So that's what's useful for that. Okay, now we have some challenge problems. These are just like a little bit more difficult than some of the rest ones. So if you're able to do these without really having a hard time, that is very impressive. And this should be the goal that you get to when it's time for the exam. So for this one, if we start with an alkene and we have MCPBA, if you're ever doing the challenge problem that's like multi-step and it might come from a lot of different chapters, I always stop and ask myself, Is this acid-base? Because that was the first reaction we learned about. Next, is this substitution or elimination? And you know that if it has a good leaving group and a strong nucleophile. Is it some kind of addition reaction to alkenes? That's what we learned about next. And then you can ask about alcohols. You can ask about radicals. I just go down the list. Like, what reaction are we doing that I recognize? And when I see an alkene, that's an addition reaction with MCPBA, it specifically makes an epoxide. And that's with any peroxy acid. And peroxy acids look like this. So it makes our epoxide, and then we have a Grignard reagent. So a Grignard reagent, that's step one. It just makes this epoxide. And you're adding it to a Grignard reagent. And whenever I have a Grignard reagent, I basically get rid of this and just make it like this minus and MgBr plus. And so you should recognize that hopefully as a nucleophilic or base catalyzed ring, epoxide ring opening. So a base catalyzed is going to attack the least substituted side. So it's going to come in here and attack. And then this bond is going to break. So now I'm going to redraw just the carbon skeleton, and I'm going to number it because I always lose my carbons. 1, 2, 3, 4. 1, 2, 3, 4. Okay, and right there on carbon 3, there is still an oxygen bonded. It's O minus because this bond broke. So the 2 electrons that made up this bond right here left that bond and went and just hung out, especially on the oxygen by themselves. And then right over here, a new bond has formed between carbon 4 and this center carbon to make your to make a carbon-carbon bond, which is what Grignard reagents do. So a bond forms between carbon 4 and this carbon right here, and then it has a methyl on each side. So one thing I will do just to make sure is I have the same number of carbons that I started with. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that looks good to me. All the right number of carbons. We have our O minus, and then you add in H plus, and you get that O minus becomes an alcohol. Now the next question asks to provide 3 methods that employ a Grignard reagent to synthesize the following compound. Well, we know Grignard reagents make alcohols when they're reacting with some kind of ketone. So a nucleophile comes in, attacks, breaks open this, and you get O minus. Or you could do an epoxide. I think it would be harder to think backwards to an epoxide. If that makes more sense to you, great. But you can just break each of these carbon-carbon bonds and make each of these the Grignard reagents and come up with 3 different methods. So whatever makes the most sense to you. I'm going to say I could have one that is MgBr, and this is the thing that attacks. And I started with a ketone that has a methyl on one side and this carbon chain on the other. So this is 1, 2. We could break this bond right here, and it could be CH3 MgBr. And we have a ketone that has the benzene ring on one side and this carbon chain on the other. Or we could do the Grignard reagent be this 1, 2, 3 MgBr. 1, 2, 3, and it attacks right there. So any of those would be appropriate. If you can figure out the epoxides, if you want to think backwards that way, I'd be impressed. I don't have the brain power to do that on our snow day week. Okay, and then last but not least, I think this one's really challenging because I look at this and I see this ketone disappears. So I'm like, well, how do I turn a ketone into basically just a methyl group, right? It's not like it goes away completely. It turns into a methyl group and there's a double bond. And we haven't learned a way to do that. So then that makes me think it must be multi-step. So we do know one way to make a double bond appear, and that's if you have an alcohol. So I'm just going to go out on a limb here and say maybe we had an OH here and an H here, and H plus H2O and heat, we did some kind of acid catalyzed dehydration. And we do know how to go from a ketone to an alcohol. And in this case, it's not just a ketone to an alcohol, which would be a standard reduction, but you add in a new carbon-carbon bond. And what do we think when we see carbon-carbon bond happening? Grignard. So I think we have CH3 MgBr to make this turn into an alcohol with a methyl group, and then it undergoes acid catalyzed dehydration. And whenever you have come up with what you think will work, then I always go and try to work it out. So if I did that, that's true. The CH3 would form, it'd be O minus. Oh, and then we'd also need H plus to get it to the alcohol. See, I always forget that. So it's good that I decided to work it out. And then if we have an alcohol and we add acid and heat, it will do an acid catalyzed dehydration. That's basically just an E1 reaction. And that seems to work. One thing that I always do is work it forwards after I work it backwards. So I initially saw that and thought, oh, I think it's just a reduction. So we have this and LAH, and that gets us to an alcohol and this, and then we must do an acid catalyzed dehydration. This is what I thought initially. And then I realized that if we did that with acid catalyzed dehydration, the double bond that forms is right here, and we're missing a methyl group. So if you work backwards and you think you know, then always work it forwards again, because you can mix yourself up and be missing something. And when you work it forwards, which you're more used to doing and more used to seeing, it will be easier. So after I do my retrosynthesis, I then always do my forward synthesis, if that makes sense. Okay, well, I hope that was helpful to y'all. If you have any questions or anything specific you want me to go over, please feel free to reach out and I will make a video about it. Happy studying!